Have you ever wondered what would happen if everything came to a standstill, if all motion ceased? Today, we're diving into the icy depths of a concept that pushes the boundaries of our understanding of the physical world: absolute zero. This isn't the kind of cold you experience on a brisk winter's day. No, we're talking about the absolute limit of cold, the lowest point on the thermodynamic temperature scale, quantified as 0 Kelvin. In terms of more familiar scales, that's negative 273.15 degrees Celsius or negative 459.67 degrees Fahrenheit. Absolute zero is a cornerstone of low-temperature physics, a theoretical point where all classical motion grinds to a complete halt. This means theoretically there would be no thermal energy, no heat, no movement. It's the idea of everything in a physical system coming to an absolute standstill. But what makes this concept even more intriguing are the potential quantum mechanical effects. As we approach absolute zero, the rules of classical physics start to bend and warp, giving way to the strange and fascinating realm of quantum mechanics. Particles could exhibit bizarre behaviors like superposition, where they can be in many places at once, or entanglement, where particles become interconnected regardless of distance. In the frigid depths near absolute zero, these quantum effects could become the norm, not the exception. Theoretically, achieving absolute zero could let us observe and perhaps even harness these quantum effects on a grand scale. But of course, this is all theoretical. The reality is that absolute zero is a formidable challenge, a scientific Everest that remains unclimbed. The laws of thermodynamics and our current technological limitations keep it just out of reach. Still, the pursuit continues because the potential rewards are enormous. Absolute zero isn't just about super cold temperatures, it's about pushing the boundaries of our understanding, about exploring the frontier where classical physics gives way to quantum mechanics. Absolute zero, a point of extreme cold where the physical world as we know it undergoes a dramatic transformation. What would it mean for us if we could actually reach this icy limit? For one, it could potentially open new frontiers in technology. Take quantum computers, for instance. These machines, unlike their classical counterparts, leverage the principles of quantum mechanics to process information. But there's a catch. They require extremely low temperatures to function effectively. So if we were able to achieve absolute zero, we could be looking at an era of unprecedented computational power. Problems that are currently too complex for even the most advanced supercomputers could become solvable. But the chase for absolute zero isn't just about harnessing quantum effects for practical applications. It's also a quest to push the boundaries of our understanding of the universe. At the heart of this chase, however, lies a formidable barrier: the third law of thermodynamics. This principle suggests that it's impossible to cool any system to absolute zero in a finite number of steps. Think of it like trying to reach the horizon. No matter how far you travel, the horizon always seems to be a little bit further away. Similarly, as we attempt to cool a system down to absolute zero, the amount of energy required to extract an equivalent amount of heat increases exponentially. It's a pursuit that becomes more difficult the closer we get, much like a paradox. But it's exactly this kind of challenge that often spurs scientific breakthroughs. The journey towards absolute zero has already led to the development of technologies that have revolutionized our world, from magnetic resonance imaging, MRI, used in medicine, to the global positioning system, GPS, that guides us in our everyday lives. So, while absolute zero may currently be an elusive frontier, it's one that continues to inspire scientists and researchers around the globe. The chase is far from over, and who knows what exciting discoveries lie just beyond our reach. Achieving absolute zero is a tantalizing prospect that continues to challenge and inspire scientists. Let's take a leap of imagination and envision a world where absolute zero is attainable. In this hypothetical scenario, the consequences would be nothing short of profound. Firstly, we'd encounter a zero energy state. This is where the system's energy reaches its lowest possible value. If you think of energy as the currency of the universe, we'd be looking at a world where the bank is completely empty. But far from being a state of bankruptcy, this could lead to a state of perfect order. Imagine materials with structures so flawless they redefine our understanding of perfection. The technological applications of such materials could be limitless, from super strong alloys to perfectly efficient solar cells. Next, we'd see the liquefaction of gases. Right now, many gases, such as helium, can only be liquefied at or near absolute zero. In our hypothetical world, these gases would exist in liquid form. This could open up new ways to store and transport these gases more efficiently, perhaps even leading to new forms of matter entirely. The implications for fields such as energy storage, space travel, and medical technology are exciting to ponder. Finally, we'd witness the emergence of pronounced quantum mechanical effects, those quirky behaviors like superposition and entanglement that particles exhibit at super low temperatures. In a world at absolute zero, these effects could be the new normal. Technologies based on these principles, which currently exist only in the realm of science fiction, could become a reality. Imagine teleportation devices or room temperature superconductors. A world at absolute zero could be a playground for the kind of physics that would make even Einstein's head spin. In a world at absolute zero, we could witness the laws of physics as we know them turned upside down. So while the pursuit of absolute zero continues, let's not forget to dream about the possibilities. After all, it's these dreams that fuel scientific progress. Despite the fascinating possibilities, absolute zero remains elusive. This doesn't mean we haven't tried or won't continue to strive for it. It's just that our current scientific understanding and technological capabilities impose certain limitations. Let's revisit these challenges. The third law of thermodynamics, a fundamental principle of nature, suggests that no system can reach absolute zero in a finite number of steps. As we push the boundaries, trying to get closer to this absolute limit, we find that the energy required to extract an equivalent amount of heat increases exponentially. This exponential increase is not just a minor inconvenience, it's a gargantuan obstacle, like trying to climb a mountain that grows taller with every step you take. It's not just about the energy, the equipment, the time, the resources all become insurmountable barriers as we inch closer to this elusive limit. And even if we could theoretically cool a system to absolute zero, maintaining that state presents another set of challenges. Any heat transfer, even the smallest quantum of energy, would raise the temperature above absolute zero. This means we would need to perfectly isolate the system, an isolation so perfect it defies our current understanding of physics and engineering. In essence, the journey to absolute zero is a journey against the natural direction of the universe. It's a journey against entropy, the inherent tendency of nature towards disorder. In a way, absolute zero represents perfect order, a state where every particle is at rest, a state contrary to the dynamism that defines our universe. But even within these limitations, we have made significant progress. We've cooled systems to fractions of a Kelvin, explored the fascinating realm of quantum mechanics, and pushed the boundaries of our scientific understanding. These ventures into the extreme cold have led to breakthroughs in fields like superconductivity and quantum computing, proving that the pursuit of absolute zero, even if unattainable, is a worthy endeavor. For now, absolute zero remains a boundary, a tantalizing point on the thermodynamic scale that continues to elude our grasp. But who knows what the future of science and technology holds? As we continue to push the boundaries, we might just find a way to reach, or at least get incredibly close to, this ultimate limit. So, where does this leave us in our icy exploration? We've journeyed through the enigmatic concept of absolute zero, the theoretical limit where all classical motion ceases, leading to a complete absence of thermal energy. We've explored the tantalizing quantum realm that could potentially unfold at such extreme temperatures, where particles could defy classical physics and exhibit behaviors like superposition and entanglement. We've also considered the technological revolutions that could be possible if we ever managed to reach this absolute limit, from quantum computers with unprecedented computational power to flawless materials. However, we've also encountered the formidable scientific barriers, especially the third law of thermodynamics, which makes our pursuit increasingly challenging. We've even dared to imagine a world at absolute zero with all its profound implications. The quest for absolute zero, while still a far-off dream,